Let's learn about operations with radicals. Here we have the van sign, which is really a square root of the answer. We are starting our new semester. We're going to start with some vocabulary. We'll add, subtract, and multiply, and then we'll get some practice. For our radical vocabulary, the bar itself is called the radical. The number underneath is called the radicand. And the number that we tuck in there is called the index. If there is no number, that's an assumed 2, which would be our square root, which we're going to spend most of the time with. You could have an index of 3, an index of 4, etc. And this means the cube root and the fourth root. But when we have a square root, we don't usually write that 2 there, but it is called the index. So we've just been practicing the quadratic formula. We had some square roots in there, so we've been simplifying. Simplifying the square root of 20, you want to ask yourself what is the largest perfect square that is a factor of 20, and that's going to be 4. So square root of 20 is square root of 4, square root of 5. I'm going to suggest you write this perfect square first. So we have the square root of 4, which is 2, times the square root of 5, and that's your answer. Some kids might write 5 and then 4 and then call it 5 root 4, but that is not correct. So that's why I like you to get in the habit of writing the perfect square first. So what's different here is now we have the x squared. So we're going to simplify the 20 the same way we just did, and then we'll deal with the variable. Remember, this 20 is not attached to the x, it's just multiplication. So I'm going to break this up into the square root of 4 times the square root of 5 times the square root of x times x, because that's what x squared means, is you have 2 x's there. So the square root of 4 becomes 2. When we have an index of 2, that means we want to take things out in groups of 2. And when I take them out, that's going to be one group. So it's like x to the 1. So I can take out one group of x's here, so it comes out as an x. And then I have the square root of 5 left over. That's my simplified answer. When you're taking the square root, you should look for pairs of variables. So here we go. I have a 5 on the outside. I'm going to do the square root of 32, and then I'll take care of my variable. So the 5 gets carried down. I want to think of the largest perfect square in 32, and that would be 16. So I'm going to break this up into the square root of 16, the square root of 2, and then I'm going to write out 7 x's. The square root of 16 is 4, and anything that comes out gets multiplied by a number if it's already there. With my x's, I have 7 of them, and I want to think of my index as 2, so I'm looking for groups of 2. How many groups of 2 do I have? 1, 2, 3, with that x left over. So that means I can take out 3 x's, but not 3x, not like that. We're taking out x cubed. So I now have 20 x cubed, and then whatever's left over stays in the radical bar. So that's my 2, and that's my x. And that's my simplified answer there. So let's try these. The square root of 25 is 5. X to the 6 is 6 x's looking at pairs, and we have 3 of them, with nothing left over. So there is no radical left. That simplifies fully. In example 5, the square root of 81 is 9. There's a 2 already, so 2 times 9 is 18. And then I have x to the 14. Well, there's 7 groups there, and that is fully simplified. I have a 3 on the outside and an x squared, and then I have to simplify the 200 and simplify the x to the 5. So I'm going to carry down the 3x squared. The largest perfect square in 200 is 100. It's also multiplied by 2, and then I have 5 x's. So the square root of 100 is 10. 10 times 3, so that becomes 30x squared. I can take out 2 groups. I already have 2 groups outside. So x squared times x squared is x to the 4th. You can't really tell a lot from that because you don't really know if I did 2 plus 2 to get 4 or 2 times 2 to get 4. So if this was x squared times x to the 3rd, well, that means I have 2 x's, and then I have 3 x's, so I have 5 x's. So the rule for exponents is you add them when you're multiplying. When you're multiplying the same base, you add your exponents. So I have an x squared. I'm going to take out another x squared. So this becomes x to the fourth. And then I have that square root of 2 left. Let's switch over to adding and subtracting. We need to know when can I do it and how do I do it. And then we'll look at multiplying. So just taking a look here at these two examples. One is ready to do more work with and one is finished. The example 7, you can't do anything more. It's just done. You cannot combine a square root of 2 and a square root of 3 and call it square root of 5 or square root of 6. They are not the same, so you cannot combine them. It would be just like if you had x plus y. You can't squish them together. However, in example 8, they both have a 5. They have the same radicand, so we can add those together. I have one root 5 and another root 5. Therefore, I have 2 root 5s. Notice I didn't change my radical. It just stays that. And it's the same grouping. So you are basically combining like terms. So when can you add or subtract? When you have the same radicand. So we say like radicands or same radicands. So on both of these you can. So go ahead and add those and subtract them. In the first one, I have 3 groups and 10 groups. Therefore, I have 13 groups. And my group happens to be the square root of 7. Here, my group is the square root of 5x. They're both exactly the same, so I can combine them. It is subtraction, so 8 minus 3 is 5. And I have 5 root 5x. So sometimes they're not going to be the same, but I don't want you just to stop here and say, oh, I can't do it. You need to simplify first. I will give you a hint. If this one is already the square root of 5, my bet is the first one can probably get broken down into the square root of 5. So on your calculator, if you do 180 divided by 5, you're going to get 36. So 180 can be broken down into the square root of 36 times the square root of 5. Well, the square root of 36 is 6, and I already have a 6 on the outside, so that really becomes multiplication. I have 36 root 5s plus 9 root 5s, which is 45 root 5s. Subtraction, we need to simplify first. 10, that can't be simplified anymore, but 40 can. So I'm just going to carry my first part down. And then 40 can break up into the square root of 4, the square root of 10. And then I have 3 times 2, because the square root of 4 is 2. So that part ends up with 6 root 10. Now I have both of them have the same radicand. So negative 3 minus 6 is a negative 9 root 10. So a little bit harder, we have our variable here. We have to simplify this. Nothing can be done with that. We have to simplify this and we have to simplify that. So 98, we want to think of the largest perfect square in 98, and that's going to be 49. So I can break this down into square root of 49, square root of 2x, because I know that that x is going to stay and I know the 2 is going to stay. So if I know that I'm going to have a 2, my bet is I'm probably going to have a 2 here. So I want you to do 162 divided by 2 on your calculator. You're going to get 81. So minus 6 times the square root of 81 times the square root of 2 times the square root of 3 of my x's. Well, I can take out an x. One group takes out an x. So I'm going to simplify up the first part. I have 7x times the square root of 2x minus 6 times 9. So that's 54. I can take out this x here, and I'm left with a 2x in my radicand. My radicands are exactly the same, so I'm going to do 7x minus 54x. You can do that. You can do it on your calculator. Don't drop your x's. So we get negative 47x with the root 2x. And that's your simplified answer. Let's switch over to multiplication. This is a true statement. The square root of 2 times square root of 7 equals the square root of 14. So I'm asking what you notice, and perhaps you notice that we don't have the same radicands anymore. You don't need them when you're multiplying. You can multiply anything. So you can multiply different radicands, and then you always have to simplify, because usually when you're multiplying, you're making something bigger, and then when you simplify, you have to make it smaller. So this one's finished. Square root of 2 times square root of 7 is just square root of 14. It can't be simplified. But let's try something like this. So square root of 2, that's already simplified. Square root of 40, we can simplify to the square root of 4 times the square root of 10. The square root of 4 is 2, so this becomes 2 root 20. Notice I multiplied the 2 and the 10. Well, now 20 has a perfect square in it, so we can do 2 root 4 root 5, so that's 2 times 2 root 5, which is 4 root 5. That's your fully simplified answer. Another way to do this is just to multiply straight off. So I can do 2 times 40 and get the square root of 80. And then I can simplify, finding the largest perfect square is 16. And then we get 4 root 5. So either way will get you the same answer. And here we have our last example. The 2 is not stuck to the x. We are multiplying. So you can multiply the 2 times the 9. Do the 2 times the 9 and we get 18. And then we have 4 x's and 3 x's, which means we have x to the 7th. So that becomes x to the 7th. But I need to simplify. So the 18, that has a perfect 9 times square root of 2. And then I have my 7 x's again. I can take out 3 groups, and I have 1 left over to go with that 2. So this becomes 3 from there. 1, 2, 3, so x cubed times the square root of 2x. That's my final answer. We ran out of class time, so you don't have to do the Desmos. We'll get you signed in with Delta. Operations with radicals has 15 problems, and then you can finish watching the video on graphing radicals.